distinct pleasure to introduce Professor Kerstin Perez at MIT, who's going to give our colloquium today. Kerstin began, well, not even began her physics career, continued her already burgeoning physics career as a graduate student at Caltech, contemporaneously with myself, working on the nefarious Atlas experiment, for those of you who may be familiar with that. Boo, exactly. Once Kerstin had essentially conquered the LHC landscape, she graciously left the remaining scraps to her lesser colleagues, such as myself, and moved on to much greener pastures as an NSF Astronomy and Astrophysics Fellow at Columbia University, where she began working on the New Star and also GAPS experiments. From there, Kerstin was then junior faculty at Haverford College, and then she was poached by MIT, where she currently holds her contemporary posting, and it's really my pleasure to hear her tell us a little bit more about cosmic ray anti-nuclear searches with GAPS experiment. Kerstin.
Thank you. Thank you for the introduction. Thank you for having me here. Thank you for both the coffee and the coffee mug that I'm using to drink out of right now. This is my first time in Kansas, and it's been really lovely so far. Can everyone hear me? Is the mic okay? Great. Okay, so as Chris said, I'm going to be talking about cosmic ray antinuclei as a signature of dark matter. And I'm going to be talking about that in particular in the context of the experiment I work on, which is called GAPS. GAPS, all right, we're looking for cosmic ray antinuclei. That tells you automatically we want to be up above the atmosphere. We are not lucky enough to be a satellite yet, and what that means is that we are an Antarctic balloon experiment. We're getting ready for our first balloon launch in about 2.5 years from now, late 2020. In case you're wondering how high up is a balloon that flies from Antarctica or any of these balloons, this photo you're looking at right now actually came from a digital camera that a postdoc on our prototype flight, which flew from Japan in 2012, graciously duct taped to our balloon instrument. So this is the view from 33 kilometers up in the air as seen by the prototype GAPS experiment. So you can see it's not quite space technically, but it's pretty space-ish. All right, so this is that's what GAPS goes up on. And that's another reason why balloons are better than the LHC, because you get to do stuff like duct taping cameras, digital cameras you buy on eBay to your balloon payload. Okay, so I'm going to be talking about searches for dark matter. That's going to give you the context for the cosmic ray antinuclei. And the cosmic ray antinuclei I'm going to be talking about are antiprotons, which are probably the most familiar of the cosmic ray antinuclei I'll talk about. I'm going to touch on those. And I'm going to touch on antihelium as well in the context of kind of recent results. But really the main purpose of this talk is going to be to talk about antideuterons. So an antideuteron is an antiproton, antineutron pair in a nucleus. And what I want to do is motivate why that's such an appealing signature of dark matter and what kind of unique sort of advantages it has over maybe other cosmic ray signatures of dark matter. Then I'm going to zoom in and talk about the experiment that I work on, the GAPS experiment, or General Antiparticle Spectrometer. It's not a great name. I'm going to give you that one up front. You can ask me the history maybe after the talk. And I say it's not a great name because we're really not general at all. In fact, we're the first experiment ever that's optimized specifically for these low-energy antinuclei signatures. So we have a little bit of a collaboration/competition with AMS, which is up on the space station, but we're really the first experiment that's optimized just in this right energy range to do these antinuclei searches. The reason that we're optimized is because we have a totally different detection technique than is used by AMS or really any of the other cosmic ray balloon experiments before, so I'll talk about that. And I can't move on without talking about the heart and soul of the experiment and this detection technique, which is the lithium-drifted silicon detectors, which is what I work on. And then as I said, this is a future experiment, so I'm going to tell you kind of where we lay right now, what the groundwork is for the next couple of years, and when you can expect to hear more from us. Okay, so as an extremely brief introduction, I'll say at this point we have, and have had for quite a while, overwhelming astronomical evidence that there's about 5 times more dark matter in the universe than there is the typical baryonic matter. And we know that because we have observed its gravitational interactions. So we've looked at the rotation curves of, say, stars within galaxy disks. We've looked at the rotation curves of galaxies within clusters. We've gone out and used gravitational lensing to measure and map where the dark matter is. And then, of course, we get our most precise measurements of how much dark matter there is on giant universe scales from looking at really large-scale structure measurements like come from the CMB. So in some sense, when we talk about detecting dark matter, we already have detected dark matter because we've detected its gravitational interaction. But as Chris said, I come from a particle physics background, so when I talk about detecting dark matter, what I mean is looking for new kinds of matter, which to me means looking for some new particles that come from beyond the standard model. And so if you're going to look for new particles beyond the standard model, you can ask, well, what do you need this new particle to, what properties do you need it to have? So you know automatically that it needs to interact with gravity. That's how we know it's there. It shouldn't couple too strongly with the strong force of the electromagnetic force. That's because otherwise we would have seen it by now, and or it would affect the clustering behaviors that we see. And it should be, I'll say, non-relativistic-ish. Again, that's to make sure you get the right clustering, large-scale clustering properties that we actually observe. So while you're doing this, while you're making up a new particle to be dark matter, the way that we typically think of looking at dark matter candidates is we say, well, while we're making up a whole new particle, let's see if we can also solve some other problems in the standard model. So say your CP violation or neutrino masses and oscillations or your hierarchy problem or something like that. And that is how you get the sort of big classes of dark matter particles that we look for. So in this talk, I'm actually not going to talk about axions or sterile neutrinos, though I'm happy to chat with you afterwards, as some of the other work I do looks at these particles. But I'm really going to focus in on WIMPs, or weakly interacting massive particle, as a very generic dark matter candidate. And like I said, I'm going to be talking about WIMPs causing cosmic rays. So as a really brief sketch, how does that work? What that means is I'm looking for some dark matter particles somewhere way out in the galactic halo. And I'm going to look for them to annihilate or decay, just generically interact via some new beyond the standard model physics. And I'm going to be agnostic about what that is. I'm going to call it a black box. Throw in your extra dimensional theories, your Kaluza-Klein, your supersymmetry, whatever makes you happy. The point is, on the other side, what you want to see coming out is some standard model particles. Now, depending on the standard model particle, this could be rather straightforward. Maybe you just get an electron directly out of here, or you get a photon directly out of here. Or it can be more complicated. It can be something that hadronizes, decays, and then gives you more complex particle candidates, say an antiprotons, antideuterons, antihelium. But that's the generic signature you're looking for. And then you want to build something that means that you can detect this stuff here on Earth. And now if you look at this, you see you got a lot of different possible candidates that you could look for. So there are a lot of different experiments that are doing exactly these kind of searches. And really all of these experiments are measuring the same thing. So they're basically making this plot. You want to plot up the flux, or you count whatever particle you want to look at. Say I want to look at positrons. So I count up how many positrons do I see as a function of positron energy. And then I have some expectation. I say, well, standard astrophysics, all the other stuff in space that's not dark matter that I do understand, that should give me something like the blue line. And this blue line can move up or down depending on what particle you look at. If you happen to be pointing at particular objects, it can go higher or lower, things like that. And then what you want to look for is something like red. You want to look for a bump, a line, or a wiggle on top of this that is not consistent with this background, that comes from something like dark matter annihilation or decay. And here I've drawn annihilation, which is more like a bump. Now the strength of this bump can depend on, of course, which particle you're looking at, as well as the cross-section for this to happen, how much dark matter you're looking at, and also how efficiently you take that particle from wherever it was created way out in the galactic halo, how efficiently you get it to you here on Earth. This is called the propagation process. So this is basically what all these searches are looking for. And if you go back even in just the very recent past, you see a whole lot of tantalizing plots like this that look an awful lot like we expect. So here's the first one. This is looking at gamma rays coming from the center of our galaxy. Center of our galaxy, we expect a lot of dark matter. What do we see? We have some expectation that's steeply falling. We see a bump on top of that that's consistent with annihilating WIMPs that are sort of canonical WIMPs, tens of GeV, say. You say, aha, looks a lot like dark matter. Problem is, it also looks a lot like pulsars. So maybe it's saying you just don't understand your astrophysical background all that well. You can also go over here, you can look at antiprotons. This is coming from AMS now. And in antiprotons, there's a little bit of evidence down here at the lowest energies for there being a little bit of excess that again looks like this bump on top of some steeply falling spectrum. The issue here is, well, maybe it's just that all the antiprotons that get made are more efficiently propagating to us. Okay, so maybe we don't understand how these cosmic rays are moving towards us all that well. Then last but not least, you can look at positrons. So this is the same plot as a function of energy for positrons. Again, you have the expectation before the measurement was made, and this is now the AMS measurement. I believe this is the most recent from 2018, and you see a big whopping hump up here that's consistent with TeV scale dark matter models with enhanced annihilation cross sections. Again, you say, aha, that looks a lot like dark matter, but again, you could say maybe there are some nearby pulsars. Pulsars are almost always the problem. Maybe there's more pulsars than we thought, and maybe they're also really efficient at getting their positrons to us from the pulsar. So again, maybe you just don't understand your background all that well. So a kind of a confusing picture, but let me pick out 3 main points from this. Point number 1, cosmic rays are full of surprises. Pretty much anytime you go out, you build a new experiment to look for a new cosmic ray signature you haven't looked at before, you see something that you didn't really expect before you launched the experiment. 2, those surprises are difficult to interpret primarily due to these large and uncertain astrophysical backgrounds. You can see, especially in the case of the antiprotons, your predicted astrophysics it's really even hard to see on the log scale how that bump exists. And then 3, if you really want to claim a detection, you don't need just one of these signatures to be right. You need to look at a lot of different signatures and have all of them be consistent with each other in order for people to start to believe you. So those are the 3 main takeaways, and what I'm going to lead into is antideuterons. Why are they so appealing? Well, the reason antideuterons are appealing is that they give an essentially astrophysical background-free signature. So you're transforming this from looking for a bump on top of some big background to looking for a handful of events that you really believe are antideuterons. And if you find those handful of events, you're certain you're seeing some new physics that is not expected from standard cosmic rays. Okay, so that leads me into talking about our antideuterons, antiprotons, and antihelium. Yes, I'm getting there. So let's talk about antideuterons. What is an antideuteron? How the heck does this thing even get made from a dark matter process? Well, let's go back to our picture of how you make a cosmic ray from dark matter. In this case, I sketched out annihilation. You could think of decay in some models too. So you take your dark matter particles somewhere out in the galactic halo, you throw them into your black box, some new physics, and what you want to have in this case come out of the other side of that physics is essentially something that's hadronically interacting. So you want, say, your bosons or your quarks, something like that. You want something that then is going to shower and decay and then hadronize. So from this one particle, you get a jet of particles. This is going to hadronize or clump up into some steady particles. So out of this one incident, say quark or W or something like that, you get a whole shower of, say, protons, neutrons, a whole bunch of pions. And sometimes you'll get an antiproton, and sometimes you'll get an antineutron, and sometimes that antiproton and antineutron are close enough together in momentum space, they coalesce and give you a stable antideuteron nucleus. So this is your picture. You have dark matter particles annihilate. They give you a jet of standard model particles, some of which can make an antideuteron. Yes?
I'm sorry, I'm missing something.
Yeah.
I don't quite understand why that's a black box. It seems like if you take dark matter and dark matter annihilation that hadronizes, why isn't it just like any standard model particle-antiparticle hadronization?
Because it's necessarily requires beyond the standard model physics because you're talking about a particle whose interactions are not currently described by the standard model. So you need something that would give you something like a SUSY interaction that's going to give you a quark-antiquark pair at the end.
Right,
but that's the only thing that's meant by that black box.
But then the subsequent hadronization is, I assume, identical to this.
Yes. So this is your run your Monte Carlo generator that describes hadronization how you want. That's standard model stuff.
Why it has to be dark matter? If you just throw two pair of the regular
Yes.
into the black box, you can come out with the same thing.
Yes, you can. That's a great question, leading me into my next slide. So if you look at what I just said, it doesn't sound like a great way to look for dark matter, right? Because why would I look for this antideuteron when necessarily the same physics is giving me tons of antiprotons, plenty of antineutrons, probably a bunch of pions and protons to look for too. And the reason that you want to look for an antideuteron is that the probability in the cosmic ray kinematics to make this same process mean that from standard cosmic ray interactions, you expect almost zero antideuterons in the energy range we're looking at. So let me explain that now. So that's basically what this plot is showing. Let me talk about the plot and then describe where the lines come from. So this is the predicted antideuteron flux as a function of kinetic energy per nucleon. You do that per nucleon because you want to maybe compare with antiprotons. In the blue, the green, and the kind of light yellow, these are just a few representative dark matter models that are consistent with all the known limits so far, kind of tens of GeV, a few different beyond the standard model physics processes. What's important is in the low energy range that gaps will be sensitive to. So this is less than 0.25 GeV per nucleon. In the low energy range that gaps will be sensitive to, you're sensitive to some of these sort of still viable dark matter models, but you're orders of magnitude above the flux you expect from standard cosmic rays interactions. So now let's talk about how you would make this from a cosmic ray, right? The way you would make it from a cosmic ray is say you have a proton or an antiproton impinging on hydrogen or helium. Okay, so let's think about a proton hitting hydrogen, say. If you think about what you want to come out the other side is you need a antiproton and an antineutron. But even if you just do the kinematics of, well, I have to have baryons conserve, that means you also need a couple protons, a couple neutrons. Boom, that's already telling you need actually a fair amount of energy in that interaction. So you need a pretty high energy incident cosmic ray in order to make the necessary byproducts to give you an antiproton, antineutron. You combine that with the fact that the incident cosmic ray spectrum is steeply falling with energy. There just aren't that many high energy cosmic rays. And you take that folded in with the fact the ones that do get made actually tend to be fairly boosted. So they tend to be up at a higher energy range than the low energy stuff in general. So all of these things together combine to give you a predicted antideuteron flux that's actually quite low and has never been detected from any experiment in space before. Yes?
I think a couple people have already said it, and I was anticipating it. It seems as unstable as any cosmic ray or
Yeah.
astrophysical calculation. Does the physics report measure the measurement? Does the physics report review the actual observation of antideuterons from CLEO?
Yes. Yeah. You guys are great. You guys keep leading me into the next slide that I'm going to talk about.
Make them any plus and minus. You make it like
Yeah, you absolutely make them. You make them different center of mass energy than the things that happen in cosmic rays, so it gets a little bit hard, but that's part of the difficulty of this. So what I'm showing you are, notice these predicted big bands on top of a predicted very low flux. And not just predicted, I mean, people have looked for antideuterons before. Here's the best limit from the best polar experiment. AMS has not released a limit yet, so these AMS bars are their projected possible future sensitivity based on actually a kind of out-of-date experiment design, but they're working on it as well. But so far, no one has seen an antideuteron coming from space, and we have no, in the current models of cosmic ray production and propagation, expectation to see one. But then that's a dangerous statement, as you guys keep pointing out, right? We're talking about a rare event search. We're talking about looking for a few. So you want to understand your systematics really well. So let me talk through, and they are large. Let me talk through what those systematics are. So let me go back, and these are all just systematics. Now, when I say systematic, I mean on the theory. So let's talk about how you actually make an antideuteron, right? So this idea of how you get an antineutron, antiproton to form into a stable nucleus, this is a phenomenological model called coalescence. Coalescence, the basic heart of the idea is if you have your antiproton and antineutron close enough together in momentum space, they'll coalesce and give you a nucleus. And the name of the game is then you make some assumption about how are those antineutrons and antiprotons distributed in your interaction, and then you correlate it with experimental collision data. Now, there's a couple of subtleties. There's a lot of subtleties in this. One is up until actually only a few years ago, maybe 5-6 years ago, what most people did is they just said, we're going to assume uncorrelated isotropic distribution of this M bar and P bar. Now, of course, it's really not that well motivated of an assumption, right? If I think that this incident particle is, say, a heavy quark, I expect a very different distribution in both momentum, time, and space of these byproducts than if it's, say, a light quark. And so the next step has really been to use Monte Carlo methods to fully describe all the correlations that come out of this, what I threw in this hadronization cloud that comes from your Monte Carlo generator. Still, you tune this to experimental data, and you get some rough agreement, but you can see there's pretty big uncertainties here. And in fact, this uncertainty goes not just as this value of P0, but as about P0 cubed. Altogether, this gives you this choice of coalescence and hadronization model. Of course, these are coupled now because you have to choose both a coalescence model and the hadronization model at the same time to get the correlations right. That gives you d-bar sensitivity factors by a factor of about at least 5 in either direction, plus minus a factor of 5 that you'll see. And that seems bad, right? But we're not done yet. There's worse. Now you made your antideuteron. You have to get it to us here on Earth. This is what's called a propagation model, so a galactic propagation model to be particular. And what that galactic propagation model does is it models the galaxy as this thin disk of material, and that is stuck in this thick diffusive halo of dark matter. And then you try and use tune parameters to describe the diffusion within the dark matter halo as well as within the disk of the galaxy. The annihilation you get within the disk of the galaxy, and that one, of course, is very important for something relatively unstable like an antideuteron nucleus, and then convection currents that push it out. So what you do is you come up with these models with all these parameters. Luckily for us, the theorists tend to cluster these into nice models called, one of my favorite names for models, max, mean, and min. It actually makes sense this time. Max gets you the most predicted particles. It's easiest for the particles to get to Earth. You see the most. Min has the least predicted particles making it to us here on Earth. And so you come up with these models or variations on these models, and you tune it to cosmic ray data. Right? You tune it to what you actually measure. In particular, you constrain it to secondary to primaries, like boron to carbon is a very important one, and that's one where the recent AMS measurements have been very impactful and helpful. So even within all this, after you've tuned, you still end up with uncertainties on the factor of an order of magnitude, just due to the propagation. So if you look at what's happening here, let me explain this. So this is the predicted antideuteron flux for 20 GeV dark matter, kind of vanilla going into BB bar, just an example. The black line is what you would expect to see in the medium propagation model. The max propagation model would be almost an order of magnitude higher. The min propagation model, notice it's not quite, it gets kind of confusing, right? Like why is it below here and above here? The reason that they don't just track max, mean, min is because you have to make all of this consistent with other cosmic ray observations. Right? So it twiddles things a little bit. But what you can kind of take away is that in the low energy range, which is where GAPS is, these propagation parameters are the most important. Right? It's easier to annihilate and deflect these light stuff than it is the more energetic stuff. So you end up with something like a factor of 10. That's the bad news. The good news is recent cosmic ray data really disfavors this min model. So you really do expect to see something more like the mean to the max than you do like something that goes below it, like comes from the min propagation model. So that's sort of the good news. But you're also not done. There's one more important thing to keep in mind. And that is you're not just getting, you don't just have to propagate through the galaxy, you also have to propagate through the solar magnetic field. So the solar magnetic field of our own solar system. And not only that, that's not stable with time. So that solar propagation varies on about 11-year timescales. And this makes, when you're doing these low energy cosmic ray measurements, this makes measuring, if you want to compare, say, antiprotons, antideuterons, this makes measuring at the same time incredibly important. Because if you measure just off by a couple years and you're trying to compare that data, you have to fold in a lot of assumptions about what the solar modulation was and how it was different in those two time periods. So all in all, it's complicated. But even with those big uncertainties, and in fact, the dominant uncertainties, the propagation uncertainties, are what was plotted in those bands that I showed on the antideuteron plot. So those were already kind of in the picture I showed you. Even with those big uncertainties, this is still a fairly generic signature that could probe realistic dark matter. So what I showed here, I don't want to get bogged down in particulars of different models, so I just chose one, I think, very interesting light dark matter model and one, I think, very interesting heavy dark matter model. So what's shown here on the left, this is the annihilation cross-section as a function of dark matter mass. The orange lines are the sensitivity of gaps for the different propagation scenarios. So the way you read this is gaps would detect or exclude anything above those orange lines, depending on which propagation scenario is right. And what you can see here in the blue, this is the region that's predicted both by that Fermi gamma ray galactic center signal that's been around for about a decade, as well as predicted by some of these low energy antiproton stuff. So this is telling you that these antideuterons are going to probe this low energy tens of GeV dark matter signature that has been impossible to sort of detect or exclude using other things. Look over here on the right. On the right, I'm talking about heavy dark matter. So this is the antideuteron flux as a function of GeV per nucleon. And what's plotted here are these like multi-TeV dark matter models with enhanced annihilation cross sections. This is for the min propagation model. This is for the max propagation model. And so what this is showing you is for sort of optimistic propagation scenarios, you're sensitive to exactly the same kind of dark matter candidates that are being put forward to explain the AMS high energy positron excess. So this antideuteron, although it has attendant systematic theoretical uncertainties, is actually kind of a generic signature to probe some of these more interesting dark matter models. Okay, that was antideuterons. So there's another caveat on antideuterons that's really important. If you think you're going to see something in antideuterons, you also better make sure that it's consistent with what you measure in antiprotons. Because antideuterons are rare event search. Antiprotons we measured, we see a lot of them. So this is a measurement, what's shown here is the Pamela data, and this is kind of old AMS data, so this is from 2015. This is, I believe, antiproton to proton ratio as a function of kinetic energy. What this is really useful for is that this gives you another lever arm on all the propagation that's hitting your antideuterons, in particular the solar, if you can measure it at the same time. So this data has been looked at and is consistent with sort of what people saw in positrons, which is that it disfavors sort of the min propagation, gives a slight preference for the max propagation. Then, if you really think you understand your propagation uncertainties, typically folding in data from other cosmic rays. There have been several analyses now for the last 2 or 3 years that believe they see an excess in the lowest energy region of the antiprotons. This excess is consistent with what Fermi is seeing in gamma rays as well, which is why people get a little excited. But again, I think you need to be really careful about this because of, in particular, these propagation uncertainties that I mentioned. That said, why are low energy antiprotons exciting for me? Well, GAPS will also measure low energy antiprotons. And whereas we're doing a search for new physics with antideuterons, we have a bread and butter. We know we're going to get hundreds of antiprotons per flight. And not only that, we're going to fill in a low energy range no one else has been able to measure before. So what's shown here, this is BESS, Pamela, and AMS. That's what's up here. And this is the 2015 AMS antiproton data, which is, I think, the most recent raw antiproton data that they gave publicly. And you can see at the energy range where these cut off is right where GAP starts to fill in. And not only that, but this is just statistical uncertainty, not systematics on the experiment. You can see that the statistical uncertainty is quite good in that low energy range, which one, low energy is most sensitive to propagation, so that's super useful. 2, you want to measure solar stuff and antiprotons at the same time you're doing a rare search, so that's super useful. That really helps you get your both experimental and theoretical uncertainties down a little bit. And 3, if you want to look at this possible signal of an excess of low energy antiprotons, if you want to up your signal to background, you want to be as low energy as possible. So this low energy antiproton measurement, once you kind of feel that you understand your propagation parameters, can also really help maybe look for light dark matter candidates.
Okay.
Yeah.
So it seems like you're suggesting that the 25-year problems with Galactic and the propagation models that have never explained data are now resolved. And so we can now trust that. Or are you suggesting that you can take those, they can take the experimental data and use those to somehow bound the
Yes. So one thing is you can use experimental data to bound, and where you're bounding and the models that you're bounding depends on what energy range you're looking at. So for example, be careful when you read propagation papers, because it really depends whether you're looking at low energy stuff or high energy stuff. So that's one. But I would say, if I zoomed out, my main point is that even if you have big uncertainties, you can still do these really interesting searches. And that with the antiprotons, you can help squeeze down those uncertainties on your new physics search. And that is really important, especially for solar, because you want to do it at the same time.
I don't want to get bogged down in this, because I know you want to get to the experiment. But how is this going to be better constrained than all the other problems that you started with? That we don't have the kind of multiple cross consistency checks that we'd like to
so there's a couple things to say here. One is I cut out one of my favorite slides because I didn't want to go too long, which is how all these different dark matter searches relate to each other. And one of my big reasons that I like to show that slide, and thank you for bringing this up, super important, students, there is no one experiment that's going to find dark matter in this field, is my opinion. You need all these different, that's why I said all these different, where am I? You need cross-correlation with all these different signatures. You need to have someone who says, I see it in this particle as well as this particle, now let's go build a collider, look for it from a collider, or a direct experiment, let's see it in a direct experiment and optimize it. I think that's without doubt. The second point I would make is that using the most current theoretical understanding of cosmic rays that we have, sort of standard cosmic ray physics that you learn in a textbook, twiddle those uncertainties, you don't expect to see any. So if you see anything in these experiments, you are seeing new physics. And I will leave it to other people to debate whether I get to go to Stockholm because I discovered dark matter, or whether I get to go write a new astrophysics textbook because I discovered something new about how cosmic rays move in our galaxy. But the point is that it's definitely new physics. Okay.
Is that a reward to write a new textbook?
That's a really good point. Maybe someone else gets to write a new textbook, I get a citation. Excellent point. Okay, then there's a last word. If I were giving this talk in 2016, I would show you this slide. I would say, take everything I just told you about antideuterons, how hard they are to make by standard cosmic rays. Now add another antinucleon. All right, that's antihelium. Obviously, it's really, really hard to make via standard processes. You don't expect to see them. In addition, you do expect to see them from hadronically interacting dark matter. But I would have said, you know what? That's a really rare. You've knocked down your cross-section by another about 10 to the 3, 10 to the 4. It's really outside the scope of sensitivity. I mean, we're talking about a satellite mission, you know, in order to be able to really see these signatures. So that's what I would have said in 2016. That was before AMS made a couple public statements. So in the past 2 years, AMS has made public several events. I believe the exact quote is, to date, they have observed several candidate events with Z equals -2 and mass consistent with antihelium. So they have for several years been talking about several antihelium-3 candidates. Most recently in 2018, they believe they have an antihelium-4 candidate event. Now, I do have to point out, this is in a higher momentum range than I'm talking about, so interpreting these for dark matter gets difficult. Not impossible, but difficult. What else could be going on? I don't know quite yet. People are writing papers and thinking about it. I'll also say this has not been a public analysis yet, though they have been talking about it for a couple years. These are events that aren't going away. I think all I'm going to say in this is that this is where, when you're doing this kind of new physics search, it's really important to have 2 experiments in the game, right? So if you look at where AMS is sensitive, which is somewhere in the energy range up here, the GAPS energy range, if it's dark matter, you expect to see even more signals. So this antihelium event is really pushing us forward to say, well, they also haven't put out an antideuteron limit quite yet, though I know the people who are working on it. It raises the question, well, what do you see in antideuterons? Does GAP see antihelium? What do we see in the low energy antiprotons? Again, because this is a team sport to try and disentangle what's going on here. Yeah?
So you say they're working on the antideuteron analysis.
Yeah.
Is there any compelling reason why this one would be seen first, or just order they get the analysis?
It's a more difficult analysis for the antideuteron analysis for AMS because they have to they have to not just separate antideuterons from antiprotons, they also get some contamination from protons, and that's like their most abundant cosmic ray species. So actually it is just a slightly more complex analysis. But I say we're working on it because one of my collaborators is actually on GAPS, is the person who's doing it on AMS, so it's coming. Okay, so that was all to get you excited for why we're going to build GAPS. All right, so here are the experiments that I've been talking about. Let me just emphasize again, what I'm talking about for antideuterons and antihelium, if we want to look at that, is a rare event search, which means what do you want in a rare event search? You want at least 2 experiments, and you want those experiments to have orthogonal systematic uncertainties. You don't want to build 2 of the same experiment and get bogged down in the same uncertainty. And that's exactly what we have for AMS and GAPS. So AMS is essentially, these are not to scale. AMS is actually much smaller than GAPS. AMS is basically a tiny little CMS up on the space station, right? It's your standard particle physics experiment with a tracker, a calorimeter, et cetera. It's been up on the space station since 2011, and essentially it uses magnetic spectrometry to do your particle identification. GAPS is fundamentally different. GAPS is an Antarctic balloon experiment, as I said before. It is essentially 10 planes of lithium-drifted silicon detectors surrounded on all sides by a time of flight, and it uses what I'll call exotic atom capture and decay to identify antinuclei. So I'm going to tell you what that means in a second. First, I have to flash who we are. This is GAPS, where main funding is out of NASA. We have substantial collaborations in Japan with JAXA and with Italy. Funding from Heising-Simons as well as NSF a little bit as well. We're PI'd out of Columbia University. And this is not quite all of us, but we're never going to probably crack the 100-person mark, I don't think. We're maybe about 50 people altogether, which is about the scale you expect for a balloon experiment. Okay, so how does GAPS find and convince themselves they're really seeing this rare antideuteron? Well, here's the cartoon. You have your low energy antiparticle, here's an antideuteron in this case, comes through, you measure its momentum with the time of flight system. Then it goes through this silicon, and this silicon's fairly thick, as far as silicon's concerned, it's about 2.5 millimeters thick. What that means is as your low energy antiparticle goes through, it's slowing down through DEDX losses. It slows down, eventually it stops. When it stops, now we're in atomic physics territory. When it stops, it forms what's called an exotic atom in an excited state. Essentially, your antideuteron, much like sort of an analog of an electron orbital, can get trapped and make what's called an exotic atom. As you can imagine, this is a highly unstable object, and it decays pretty much on our timescale instantaneously. And when it decays, it goes through the analog of electron orbital transitions. So you get X-rays of well-defined energies. Eventually, the antideuteron annihilates with the silicon nucleus. You get a shower of pions and protons coming out. So this is your event signature. Something comes in, you measure its momentum as well as its DEDX with the time of flight. It slows down, you see it stop, you get X-rays of well-known energies, and you get a shower of pions and protons. So you get a lot of different signatures you can cut on to tell you saw an antideuteron, which is good, because everything I just told you about an antideuteron is also true for an antiproton. And even for the most optimistic dark matter models, you expect about 10 to the 4, 10 to the 5 times more antiprotons than you do antideuterons. But an antiproton coming in will, for the same time of flight, stop less deep in your detector. We'll have different DEDX losses along the way. We'll have a smaller multiplicity of pions and protons coming out from the nuclear annihilation. We'll have X-rays of different well-defined energies. So again, once you combine your time of flight, your depth sensing, your DEDX, your X-ray, your pion and proton yield, you can come up together with all those variables with a rejection factor of well over 10 to the 6, which is what you need to start doing this kind of search. And I'll just say, not shown here, but you can look it out. This exotic atom technique, it's exotic atom physics, it's atomic physics. It was verified with a test beam of antiprotons at KEK. Okay, so that's sort of the cartoon of what GAPS is. What does it really actually look like? What it is essentially a 3-meter cube. And the heart and soul of it is this 1.5 meter by 1.5 meter cube that is the lithium-drifted silicon detectors. These are about 10 centimeters across, so we're going to need about 1,000 of them, order of magnitude. And these are really doing a lot. They're doing the X-ray identification, they're doing the DEDX, they're doing the stopping death, they're doing the shower particle multiplicity, they're measuring your X-rays. That's surrounded on all times by a plastic scintillator time of flight. The big performance goal for the plastic scintillator is the timing resolution. So we want to hit less than 500 picosecond timing resolution, which they have with our prototype paddles. All of this technology was verified on our prototype flight, which I showed you the photo of on the beginning. So this was a flight that launched from Taiki, Japan. It was just about 6 hours because it was an engineering flight. It had just 6 detectors and 6 planes of time of flight. The main point here was to validate our detectors and our cooling system and also to measure some background rates. That all went great. In case you've never seen a balloon launch, this is what it looked like. So around 5 a.m. is where it lifted off. At float altitude, that's the picture I showed you before. Again, it's not quite space, but it's space-ish. And it was just an engineering flight, so we were only up for a few hours. We cut down, we paid a bunch of Japanese fishermen to pull it out of the water, and we called it a day. Now the main point of this is going to lead into what I have to spend a few minutes talking about, which is my detectors. The main point of this was really, one of the main points, was to validate these lithium-drifted silicon detectors in an ambient environment on a balloon flight. If we needed a pressure vessel, we'd never make it off the ground, we'd be too heavy. So we had to prove that these would work without a pressure vessel, and they did quite beautifully. So what this plot is showing is an X-ray calibration tube shooting during flight, and then what it looked like on ground, and they looked exactly the same, as well as in a vacuum. So everything was completely consistent with temperature-dependent predictions. And that leads into, in the last 10 minutes, me talking about these detectors. I have to. Oh no. I have a picture that's not showing up. All right, I'm going to talk through it. Imagine, everyone use your imaginations. Oh, all of these pictures. The picture that used to be there of this beautiful gold-looking detector the last time I clicked through. Imagine that picture. Ha! It moved. Okay, great. Fantastic. It moved to where I want. Okay. Why am I using lithium-drifted silicon detectors, and what are these things? I think the best way to do this is compare it with something maybe you know a little better, at least what I know a little better, which is the Atlas silicon pixel detector from the LHC. This is something, one module is about 2 centimeters by 6 centimeters, and it has over 46,000 channels on it. It has that because you really want this high multiplicity, sort of high resolution tracking. Compare that with GAPS. This is 10 centimeter radius, and we have 8 channels on it. All right? We only need 8 channels because we're really just doing the tracking efficiency from this kind of rare process. And we need to be able to separate incident particles, and that's basically all we need. This is about 250 microns thick. Quite thin, right? You want it thin because you have it really close to the interaction site. You don't want to mess it up before it hits your calorimeter. We're thick, 2.5 millimeters thick. And we have to be that thick because we're trying to stop the thing. We're doing the opposite. We want it to stop inside our detector. Also, our energy resolution goals, 4K EV, that's to tell the difference between an antiprotonic and antideuteronic X-ray. That's really not that constraining in the grand scheme of things. And that's good that our performance goal isn't too bad, because we need about 10 square meters of this stuff. And I don't know if any of you have built silicon experiments before. 10 square meters of silicon is very expensive. And in fact, the silicon detectors we flew on our prototype flight that were this size cost about $20,000 a pop. And that was...
Is that why you retrieve it instead of trying to...
Yeah. And that was 7 years ago. That's why we didn't pay the Japanese fishermen that much, but yeah, we paid them to take it out. So you can do the math, $20,000 times 1,000 detectors. We can't afford that. There's no way our experiment could. And so this really brings in what makes these detectors special is the cost that we had to hit, as well as temperature and power constraints of being on a balloon. They can't take too much power because we can't dissipate that much power. They can't need to be all that cold because we can't get them all that cold. It's about minus 45 up there, but you got to dissipate some heat as well. For silicon detectors, that's really not actually all that cold, especially not for big ones like these. So that drives what we need to do. And like I said, it costs $20,000 a pop to buy them. What's a lot cheaper is to go back to the literature from the 1950s and figure out how to build them. So these are detectors that honestly people don't build that much anymore, again, because they're going after performance more like this than they are going after performance more like that. Where we gain then is that we can just kind of try to retrieve that old technology from the 1950s. So I joked, but it's kind of true. It was a lot cheaper to get a postdoc and a whole bunch of undergraduate and graduate students to learn how to build these things than to buy 1,000 times 20,000 of them. This is one prototype one. It was 2 inches across, so not quite the 4-inch geometry quite yet. But you can see at minus 40 C, which is about what we're expecting in flight, it hit that beautiful 4K EV energy resolution. So that's really great. So what I want to do, I got like 5-10 minutes left. I want to teach you how to make a $20,000 detector for, you could make a 2-inch one, about $200, not including labor, depends how much you pay your undergrads. You make the 4-inch ones for about $500-600. Again, depending on labor and how much you pay your undergrads, what kind of facilities you have access to. But I want to teach you how to do that in the last 10 minutes. Okay, but before I do that, let me just take everyone way back. Semiconducting detector basics. So a silicon detector is an ionizing radiation detector, right? And the benefit of a semiconducting detector is that it takes a relatively small amount of energy to knock an electron from your valence band up into the conduction band. Now you can move it out to your device and measure it out. For silicon, it takes about 3.6 eV, right? So if you're talking about 30K EV X-rays, which I am, divided by 3.6 eV, plus you get electrons and holes, you're not statistics limited. You get a lot of a signal. So what happens in this detector is ionizing radiation comes in. Here's your little silicon lattice just hanging out happy. It pops an electron up into the conduction band. It leaves behind what's called a hole, which is where that electron used to be, that acts like sort of an isolated positive charge. You put a bias across it, boom, you move your electron up to the positive, you move your hole down to the negative, you get a signal, you read it out, everything's great. So why is it not just this easy? Well, the problem is pretty much any silicon you buy is going to have a leakage current. So leakage current means no signal comes in, I just put a bias across it, what does my current look like? That's way too high to actually be able to do this kind of particle search. Even if you buy high resistivity silicon. So I should amend this. They do actually now make really high resistivity silicon, but you need really, really, really big voltages to deplete 2.5 millimeters, which is what we need. And we can't, again, we're on a balloon, power constraints, we can't do it. So we're back to lithium-drifted silicon. Okay, so in practice, you can't just make this usually. You can spend a lot of money on silicon, maybe, but it's a little difficult. Instead, what most people do is they look at doped semiconductors. So again, this is terminology that's going to help you learn how to build these things. There's two kinds of doping. One is p-type doping. P-type doping is, all right, silicon's valency 4, right? So it has 4 little electrons hanging out that can mate up with other electrons and make your crystal. In p-type doping, you put something like boron that's valency 3 into your lattice. That means it's missing an electron to bind. Boom, you get a free hole. And if that hole moves away, you're left with a fixed positive ion. You can do the opposite. Put something like phosphorus in there. Phosphorus is valency 5. It has an extra electron. Boom, you get an extra electron, free electron that can move away, leaves behind a fixed positive ion. On their own, not very useful. You have made your problem worse. You have put in impurities where you wanted to get rid of impurities, which is why people usually look at junctions of this p and n-type material. And at the junction, something very special happens. If you put these two things right next to each other, all the negative charge will move over to the positive side. The positive charge will start moving over to the negative side. And this charge will flow until it builds up a potential barrier so big that charge has to stop flowing. In that region with that high potential barrier, you basically what we call depleted that region of free charge carriers. So right at that junction between these two materials, you have a wonderful detector right there. Now the problem is, for me, I don't want this thin little region to be useful. I want a nice thick 2.5 millimeters to be useful. And that's why I have to do something slightly different. So that's why we look at lithium-drifted silicon detectors. All right? I think I need this like 90 seconds how you make these things. Lithium-drifted silicon detectors work in that you have lithium ions, compensate impurities in boron-doped silicon. They give you these nice thick charge-free regions. All right, let's build. You start out with a p-type doped wafer. Now imagine you're looking at this one like through the cross-section, okay? P-type, I just told you, you get a free positive hole. That positive charge can move around. That leaves the negative ion behind. You evaporate, so that's what you buy. So you buy them in boules from some manufacturer, and they're relatively reasonably priced. There's a few different manufacturers you can buy them from. You then evaporate on top of that detector, so again, you're looking at a cross-section, some lithium. Lithium's special for two reasons. One, easily ionized in silicon, which means it gives up a free electron really easily. Two, has high mobility. That means the positive ion that's left behind can move around. Okay, you can look at this and start to see what I'm about to do. We have free positive charges, fixed negative ions. We have free electrons and some positive ions to move around. I want to move these things around in just such a way that they cancel out. Here's how you actually get the lithium onto it. So this is a lithium evaporator. It's actually nothing all that complicated. You have about a tungsten boat that you heat up, that heats up the lithium. Your detector is up here. It's in a vacuum, so it puffs the lithium up, and you just got lithium on your detector. Here's the magic, the lithium drift. What you do is you apply a bias across this detector and you heat it up. You heat it up, that makes the lithium able to move fairly easily. You put a bias that tells it where to move. And what you do is over a long time period, so for 2.5 millimeters, we're talking a few days for reasonable temperatures and voltages, you're slowly pulling these mobile positive lithium ions through your silicon in just such a way. Think about what happens. Where is it going to move? It's going to want to move preferentially towards where there's, say, a negative impurity. It's going to want to compensate that impurity. Where the negative is going to want to move, they're going to want to move to where you can compensate a positive impurity. And so over these very long time periods, you build up these very thick intrinsic or charge-free regions that make nice detector with low leakage current. Again, this is actually something that an undergraduate student built, this particular drifting station. It's nothing all that fancy. You need to get it hot. You need to apply a bias. You need to monitor a few things like the current and the temperature and the bias over time. but it all works. And at the end, as I said, you get this extended charge-free region, and from there you can segment, you can put strips. I'm kind of glossing over things like a guard ring, which are necessary for these big areas. But you get these nice, this is actually a beautiful photo, you can copper stain. So here copper preferentially has plated where there's lithium. So you can see there's this nice thick lithium diffused layer from this step, a nice thick lithium drifted layer from this step, and then on the side where it didn't drift, which is over here, you don't see the lithium at all. And so this makes your detector. And it is a straightforward process. I am glossing over some minor technical details that go into really how this works. But I work with an engineer from Livermore, retired engineer from Livermore, who during the years when I was trying to get this to work, he sent me this photo because I think he thought it was encouraging. He said, oh, it's not so bad. Look, I made this little 1-inch detector in my garage. And he meant this to be encouraging, but when I was like in semiconductor facilities that were really high tech and not working, it was not very encouraging. But now that I have gotten them to work, I'm back to it's encouraging. You can do these things kind of low tech. All right, so where do we stand now? Now we're getting ready for the flight. We've partnered with a corporation in Japan called Shimadzu Corporation, who's developed the very large scale. So sort of the 2-inch was sort of proof of principle that we could build these things. Shimadzu is now building them for us. If we look as a function of shaping time, you see we're getting a full width half max energy resolution that's well below the 4K EV that we need. So this is really spectacular development. And I'll say really spectacular because this is what they typically sell. The company makes little 10 millimeter diameter button detectors. That's their bread and butter where they make their money. And with us, they've developed up to 4 inches in a little over 2 years. So it's been really rapid and successful. So that's it. These are just a couple slides talking about what we're working on now. On the detector side, we have to worry about passivation and how we're going to basically package all these things. But the main fabrication challenges are over. Now I get to worry about, all right, we're actually going to build 1,000 of these things. How am I going to test them all? How am I going to get them into an instrument? The time of flight is going very well. As I mentioned, they demonstrated already their performance criteria well under 500 picoseconds, which is great. And the cooling system, I'll say like 2 words about it. It's really cool. It's a pumpless cooling system. It's the first time it's going to be used on a non-engineering flight. The idea is this, it sounds like magic. You have thin capillary tubes. You fill it with alternating air and fluid. When it gets over to the hot side, the air expands. It drives it over to the cool side. Gets the cool side, it contracts. Boom, boom, boom. If you give it a little kick, it actually flows with no power on your balloon payload, which is really important. And no moving parts, like pumps that can fail, which is also important. But that was demonstrated on our prototype flight and in subsequent flights and lab work. So that's going. And this is where I'll end. I like to show for students how long, even though we're a small experiment, how long it can take to actually build up this thing. So back in 2000 was the first idea. So sort of working through the exotic atom physics that this kind of detection technique would work. Followed by beam tests that proved that it would work and our prototype flight. And where we are now is we're ending, we're in 2018, so our design is over and we're well into fabrication and payload integration, and we're looking at a first flight somewhere in late 2020 with ultimate sort of the sensitivity curves I was showing you in the first part of this talk, baseline for 3 flights from Antarctica. So stay tuned. That's it. Yeah.
So you talked about the solar magnetic field and how it varies on the 11, your time scales and how that can introduce a bit of uncertainty. But the galaxy certainly varies on those same time scales as well. And so I'm wondering if you can talk a little bit about how models take that into account, or the kinds of astrophysical observations, like for example, constraining the galaxy magnetic field or dust or supernova rates, things like that would help you.
Yeah, so you gain a little bit on the galactic side because we're talking about signals that are typically coming from very far away, right? So you kind of win in the averages in a way that you don't win when you're doing something like positrons, and it might be coming from really nearby pulsars, and then you really need to care. So you win a little bit on that. The rest of your question, which is sort of what else do you look at to do this, you basically look at any low energy cosmic ray that you can, which is where AMS is really important. So AMS is slightly higher in energy than GAPS will be, but they're as low as they go, and they have a beautiful super high statistics data set. that they, in their most recent results, actually are starting to actually look at timescale variations, because they've been going since 2011, and they have this really high statistic. So they're very useful in understanding, on the low energy side, how much do you expect these sort of things to change, and on what timescales do you expect them? I don't remember.
Okay.
It wasn't.
You do see a variation.
You do see some variation. It's well under the order of magnitude uncertainty that you expect for like your Mead Max model.
Right.
Yeah.
I didn't hear if you have an antideuteron beam to calibrate this at the low energy.
No one has yet made us an antideuteron beam, so we do not have that.
As we know, deuterons are awfully fragile,
Mm-hmm.
and then low energy, old-fashioned nuclear physics is awfully difficult to calculate. How are you going to know the rates of your detections in your detector to know how efficient it is with antideuterons?
So we're relying on a lot on, there's a few things. So one, in terms of dealing with the fact that antideuterons are break up, right, before they reach the experiment itself. Yeah. So that is actually our
material too.
Yes. So that is folded into one, it's folded into getting to the atmosphere. We're up high up, but we still deal with some atmosphere going on. And then two, we just deal with, it's the same way you do it at a collider, say, right? You have a different sets of Monte Carlo simulations, you have different sets of what your material might look like, and you try to bound your uncertainties on that sense. But that's basically all you can do because you don't have an antideuteron beam.
Copy a collider, it's the light, but you've got to have this thing calibrated right.
Yeah, but you also do it with antiprotons. So you don't do the breakup with antiprotons, but you do the sort of basic calibration of like, are my particles coming through the way I expect? Are they passing through the same amount of material I expect? Because you have a well-measured antiproton spectrum. You got to make sure your antiproton spectrum
How do
matches.
you know the total cross-section for a 1 MeV, 1 keV antideuteron on a silicon nucleus? The cross-section could vary.
So you mean the cross-section for breakup?
No, the cross-section for absorption for the event that you're talking about, your signal.
Well, if you slow it down and stop it and it goes through the material, then that should be near unity cross-section to make.
For 100,000 bars. And another
Not for exotic atom capture.
For a low energy neutron. Some of these things are absolutely whopping. There's
I
one in a
don't
time.
think for the process that's making the low energy antideuteron capture.
Well, you've got to go
That the
with
uncertainties.
the stick.
It has to stick, yes.
That's a low energy strong
I-
interaction process that's extremely
Yeah,
problematic.
I don't have, I couldn't point you to the papers, but I do not think that uncertainty is as large as that. I think that exotic atom physics is actually fairly well known.
Cross section has done a lot of damage to Alma Libra. The direct detection of dark matter.
Yeah.
People got all their neutron cross sections wrong
Yeah,
by 100,000 bars.
but that's a different process, right? That's a scattering process.
It's just as bad because you've got to stick that low energy.
No, because you're
cable.
stopping it. It's happening at rest. So it's actually not quite as bad.
We can talk about it.
Yeah.
More questions?
Yeah.
This is a very basic question. I'm very low level physics student. So theoretically, when it comes to dark matter, when you're looking at the different particles, theoretically, would every particle that we know have a dark matter equivalent?
Not necessarily, no. I mean, so, there are worlds in the question that you just asked. Whole worlds you open up.
I know.
No, it's not necessary that every single particle in the standard model will have an antiparticle or sort of dark matter or dark sector particle equivalent. And in fact, the thing that you're kind of teasing out that I actually think is very important and gets hidden in some of these plots that people show in dark matter plots is when people talk about dark matter searches, what we're doing is really the simplest thing typically, which is we say, we know how much dark matter there is from astrophysical observations. And we have this idea for what dark matter could be, right? It's like a WIMP from supersymmetry, or it's from some extra dimensional, or it's a stereo neutrino. And then we say, all right, let me come up with how many I expect to see in my experiment. Well, how do I do that? Let me just assume dark matter is all that one thing. It's all that one thing, all of dark matter is that one thing. And, it's not that that's necessarily wrong. It's the simplest way to do a search But it is a hidden assumption that goes into some of these plots when you'll see people make exclusions. And they'll say, we exclude dark matter below 20 GeV mass or something like that. Typically what they're doing is they're assuming dark matter is all one thing, which is not necessarily true. And they're assuming that it all goes into the particular process that they happen to be measuring. Right? Like some of these plots said 20 GeV dark matter annihilating into BB bar. There's zero reason that dark matter would have to annihilate entirely into BB bar. And there's also no reason dark matter has to be this only one particle. But it's the best we can do. It's a way to parameterize and make exclusion limits. Yeah, you got to try and come up with a way, but it's a good way to plot things, but it does hide some assumptions in there that I think are important to tease out.
One question. You have these positron excesses and gamma ray excesses. They seem to be at very different energy scale. Is there any way that those can be consistent with some kind of?
I believe the positron excess and the gamma ray excess are not consistent with each other because, in fact, the positron excess, one of the arguments against it is that it's not really consistent with antiproton data in general. You're talking about very different mass scales. And again, both of them assume that they are all of dark matter in order to get the observed signal that they see. So I don't think they're consistent with each other. Yeah.
Would you like to say something really candid and controversial about the current state of experimental results related to dark matter? What do you really think that you can actually say?
I'm happy to say my real thoughts. No, because my real thoughts were on the slide. Like my real thoughts were really what I said. I think that cosmic ray physics and searches for dark matter, no offense to LHC people, I think it's a great way to go after dark matter. You're going after dark matter at the source. Where do we know dark matter is? It's out there. If you find new forms of matter at the LHC, please do. But until you see it coming from space with the right cross-section, coming from the right places with the right density, that's how you know it's dark matter. So that's point one. Point two, if you ask me for like the general state of the field of cosmic ray physics, I actually think the last decade has been super exciting. Because people are kind of starting to expand beyond, we thought direct detection experiments were just going to turn on and you see it. That's not really how it's going. And so people really are creatively looking at all these different signatures in cosmic rays and saying, what can we learn from what's coming from space to tell us something new? That said, we keep seeing all these new anomalies. What's exciting is we keep seeing something new. We're learning something new about cosmic rays. We're learning something new about the universe. We're maybe not learning something new about dark matter, but if we're not finding dark matter, we're excluding it, right? And so I think it's very exciting that we're starting to look into all these different corners of the different sort of particles that are coming from space to figure out how can we build a coherent picture about what the physics is that's happening out there. That said, it's really, do I necessarily 100% believe any of these experiments? I would say extraordinary claims require extraordinary evidence, and at this point, none of these experiments have shown a result that can't be explained by just undiscovered standard astrophysical stuff.
Do you 50% believe any of them are showing us?
I don't think that is a rigorous statistical statement to make, so I cannot answer it.
It's basic.
So let's thanks again, Professor.